Hello and welcome to another episode of Digital Pulse. Today, we're diving into this Nexus 1.0.
Oh, cool.
Yeah, and we've got their white paper. It's all about verifiable computing at internet scale.
Wow.
Yeah, pretty ambitious stuff. So we're going to break down how Nexus works, what makes it different, and why it could be a big deal.
Okay, yeah, that sounds pretty interesting. I mean, it's fascinating how Nexus tackles some of the biggest roadblocks in zero-knowledge proofs. You see, traditional methods are like building a custom computer chip for each specific task. Effective,
Right.
but super complex and inflexible.
Yeah, like needing a whole new factory just to change a button on a shirt.
Yeah.
And then there are the newer CPU approaches like Cairo and ZK EVMs, aiming for a more general-purpose solution.
But they face their own hurdles
Yeah.
with scalability and handling those really complex computations.
Exactly. It's like those CPUs are green for basic tasks, but try running a high-end video game, and they just choke.
Oh, yeah, sure.
Nexus aims to solve this with a two-pronged approach, a vast distributed network, and a specially designed zero-knowledge virtual machine, or ZKVM. Okay, let's unpack that. First, the Nexus network. They compare it to massive volunteer computing projects like SETI at Home or Folding at Home, where millions of devices contribute processing power. But Nexus adds something unique, provable guarantees thanks to the ZKVM.
Think of it as a verifiable supercomputer, proving computations across a huge network of devices. Even your phone could be a part of it.
Wow.
This boosts the ZKVM's power, letting it handle computations that were previously impossible.
So we could potentially harness the combined power of millions of devices to solve complex problems and know for sure the results are accurate. That's mind-blowing. But what about the heart of it all, the Nexus ZKVM? It's designed to prove pretty much any computation, especially those requiring billions of CPU cycles. How does it pull that off?
This is where it gets really interesting. The Nexus ZKVM has several key innovations. One is snarkless recursion. Instead of relying on computationally expensive snarks for each step, it folds or accumulates proofs using techniques like IVC and PCD.
Okay, so instead of checking each step individually, it's like verifying groups of steps together, right? That seems much more efficient. But how does the program actually run? They mentioned something called the Nexus Virtual Machine, or NVM.
The NVM is like a simplified universal computer, specifically designed for proving computations quickly and efficiently. It has a minimal set of instructions and a straightforward way of handling memory and data, all optimized for proving those massive computations we talked about.
But wouldn't a simplified machine be limited? How can they claim to prove any computation?
That's where ZKVM coprocessors come in. Think of your kitchen. You have basic tools that work for most things, but specialized appliances like a blender or food processor make specific tasks way easier. These coprocessors act like specialized add-ons for the NVM, speeding up specific tasks without sacrificing overall performance.
So it's like having the flexibility of a basic kitchen, but with the power of specialized tools when you need them. Pretty clever. So we have this powerful network providing the muscle, and this unique ZKVM handling the proofs. Can you walk us through what happens when a program actually runs on Nexus?
Sure. First, there's a one-time setup where you can customize the machine by adding those coprocessors we talked about. Think of it like choosing your kitchen appliances based on what you'll be cooking.
Got it. So you decide if you need that extra horsepower for specific tasks.
Exactly. Then for every program you want to prove, there are 3 steps: compilation, execution, and folding. Compilation translates your program into instructions the NVM understands. Then the program runs on the NVM, generating a detailed record of every step. Finally, the folding process uses those snarkless recursion techniques to create proofs for blocks of execution, utilizing the power of the network.
So it's like a giant puzzle where each node in the network solves a small piece, and Nexus puts it all together.
Precisely. And to make those proofs super efficient and verifiable, they're compressed using a sequence of ZK snarks. Imagine shrinking a huge textbook down to a pocket-sized summary without losing any information.
Amazing. So we end up with a compact proof that guarantees the entire computation was done correctly. This all sounds complex, but they claim it's surprisingly developer-friendly, even providing an example using the Fibonacci sequence.
Yes, the entire Nexus system is open source. With tools and documentation to help developers get started, the Fibonacci example shows how straightforward it is to prove a program using Nexus, making it accessible to a broader audience. What's truly exciting is that Nexus doesn't just improve existing zero-knowledge proofs, it opens up entirely new possibilities for what we can do with computation, for example. Think about secure data sharing.
Okay, yeah, privacy and data breaches are huge concerns these days. How could Nexus help with that?
Imagine proving you've analyzed sensitive data without revealing the data itself. Let's say there's a medical database with millions of patient records. Researchers could use Nexus to prove they've done statistical analysis, finding trends and developing treatments, all without accessing any individual's private information.
So it's like getting the insights without the risk of exposing sensitive data. That would be a game changer for medical research in any field where data privacy is crucial. Are there other examples in the white paper?
Absolutely. They talk about financial systems. Auditing and verifying transactions is complex and often opaque. With verifiable computing, each step of a transaction could be proven mathematically, making the whole system more transparent and reducing the risk of fraud.
That would build so much trust in financial institutions. It could even change how we think about money and value exchange. What about areas beyond data and finance?
The white paper dives into scientific computing. This field relies on complex simulations and models, requiring immense computing power. Nexus's distributed network and efficient ZKVM could let scientists tackle problems that were previously impossible, leading to breakthroughs in areas like climate modeling, drug discovery, and materials science.
It's like giving researchers a superpowered tool to explore the complexities of the universe or the human body. What's really fascinating is how this level of verifiability could impact how we interact with the internet and online platforms.
Exactly. Imagine social media where you could instantly prove the authenticity of content, eliminating fake news and misinformation. Or online voting systems where every vote is verifiable without revealing individual choices, ensuring secure and fair elections.
Those are some incredibly powerful applications. But let's be realistic for a second. What are some of the challenges or limitations Nexus might face?
Well, like any new technology, adoption is key. For Nexus to truly revolutionize computing, developers, researchers, and institutions need to embrace it.
Right, it's like building a state-of-the-art highway. It's useless if no one drives on it.
Exactly. Building a strong community around the project is vital. They've made the code open source and provide resources for developers. But ongoing outreach and education will be crucial.
Another challenge I see is the complexity of the technology itself, even with simplified tools and documentation. Understanding zero-knowledge proofs and verifiable computing requires a certain level of technical expertise.
You're right. Making these concepts more accessible to a wider audience is essential. Educational workshops, online tutorials, and even collaborations with universities could help democratize access to this powerful technology.
That makes sense. This whole deep dive has been incredibly thought-provoking. We've gone from understanding the limitations of current zero-knowledge proof systems to exploring the revolutionary potential of Nexus 1.0 and its implications for various fields. It's clear that this technology has the power to transform the way we compute and interact with the digital world.
And we've only scratched the surface. The Nexus white paper is packed with technical details and insights. I encourage you to explore their documentation and GitHub repository for a deeper dive into this fascinating world of verifiable computing.
Yes, definitely check those out if you're interested. But before we wrap up, I have one final big picture question. The white paper mentions Nexus, aiming for a throughput of 1 trillion CPU cycles proved per second. If they hit that, what kind of computations could become possible? That we can't even imagine right now.
That's a question that really sparks the imagination. If Nexus delivers on that promise, we're talking about a fundamental shift in what we consider computationally feasible and verifiable. Imagine incredibly complex simulations that could accurately predict climate change decades into the future, or model financial markets with unprecedented precision.
Almost like having a crystal ball that actually works. What about other fields? Could we simulate something as complex as the human brain?
It's not out of the realm of possibility. With that kind of computational power, we could see breakthroughs in understanding consciousness and intelligence, leading to advancements in fields like artificial intelligence and neuroscience.
So we could be on the verge of unlocking entirely new scientific and technological frontiers. But beyond specific applications, what about the broader impact on society?
The inherent trust and verifiability of Nexus could foster a new era of collaboration and innovation. Imagine a world where scientific findings could be instantly verified, eliminating doubts and accelerating progress, or where online transactions and interactions are inherently trustworthy, reducing fraud and building stronger online communities.
It's like shifting from a world built on assumptions to a world built on provable facts. It's a powerful idea. This deep dive into Nexus 1.0 has been incredible. We've learned about the limitations of current systems, the revolutionary potential of Nexus, and its implications for everything from scientific research to our daily online interactions.
It's been a pleasure exploring this with you. If you're intrigued by the possibilities of verifiable computing, I highly recommend checking out the Nexus documentation and GitHub repository. There's a wealth of information available for those who want to learn more, and maybe even contribute to this groundbreaking project.
That's a great point. A huge thank you to our expert for guiding us through this complex and fascinating topic. And to our listeners, thanks for joining us on this deep dive into Nexus 1.0. Until next time, keep exploring, keep learning, and keep questioning the boundaries of what's possible.